All right, everyone. Section 7.3. This next section is called integration by parts. It's another method for integrating. It's going to feel a little bit like U substitution in some ways. So I'm going to do actually the same thing I did with U substitution. I'm going to start with a function's derivative and kind of work backwards just to give you the method. Again, the first 5 or 6 lines here probably don't matter in terms of taking notes. But the actual last step is the integration by parts, which is kind of helpful. It is a substitution method. It's actually a way to deal with the product rule. So if you notice, I'm starting with f times g. So if we have two functions that are multiplied together, something very simple, like sine x times x squared or something like that. It's like, whoa, what do I do? By the way, if it was sine x, I was just about to write this, which was kind of funny. If it was sine x times cosine x, you could actually do a u substitution. You can make u equal to sine or cosine because the other one's going to cancel out. So this is a way to deal with the product rule. So here's what's going on. I start with f times g. So I'm going to just take the derivative of f times g, which is f prime g plus g prime f. All that is the product rule. So I'm going to work backwards like I did with the substitution. So you might be able to figure out what's happening next. What I did is just a little algebra. I took I isolated the g prime x f of x. So just isolated this. I brought that over there by the subtraction problem. All right. Then I'm going to integrate everything. So all I did is throw an integral sign on everything here. So integral of g prime f equals the integral of the derivative of f times g minus the integral of f prime g. So all I've done on this step is a little reorganizing here just for the sake of what's going to happen later. No big deal. I just reorganized the g times f. It's now f times g. This I did the derivative. All right. The integral of the derivative of f times g is f times g. And I just left the other one alone. So now I'm going to do my little substitution here. So watch this. U is f. So that's u, that's u. Du becomes f prime. So what happens is I can rewrite this so it looks really nice. Okay. If I then work backwards and forwards on both of them. So I notice in here, here's the thing, right? I have a function, but I also need its derivative. And here I have a g prime and a g and an f prime, right? So if u is f, then du, oh, sorry, I made a little boo-boo there. I shouldn't have said this one. That's not a substitution, sorry. I wrote this a little bit backwards. Let me backtrack a little bit. This is my actual substitution. Again, none of this really matters, so don't panic too much. Sorry, I switched it around. So u is f, which means du is f prime. And then I made dv, which is a derivative, equal to g prime, which means v has to be g. If you work backwards from here, right, go this way. If v is g, then dv is g prime. The reason I just did all this is so I could make it look like this, just make it look so I can connect them all, because they're all kind of connected. Okay, so if you go back up here now, this f is a u, the g prime is a dv, the f is a u, the g is a v, and the f prime, again, is a v, and the g is a, the g, I got that backwards. The f prime is a du, and the g is a v. I just have those backwards. So basically, I just rewrote it using u's and v's so I can see it. This is called integration by parts. So if you want to remember anything, you just remember the integral of u dv. It's two things multiplied together, equals u times v minus the integral of v du. What we're going to do is we're going to take one integral, and we're going to do a substitution, and we're going to apply this property here, this integration by parts, and then we're going to have another integral. And what we're going to do is we're going to have the other integrals easier to figure out. All right. The trick is, remember, we're starting with some sort of product. So any problem I start with, so again, just like last week, I got 1, 2, 3, 4, 5, 6 different problems. So I'll probably do 2, maybe 3. I'll start with this most basic one. So you see a product, right? So the idea is this. We have to start by picking my u and picking my dv. So here's where things get a little tricky. Because if you remember the formula, let me write the formula down here again. U dv equals uv minus the integral of v du. So you can see it. I'm going to pick my u and my dv because that's my starting point. And then once I pick my u and my dv, I need to find my du and find my v. So I'm going to have to take the derivative of u and the antiderivative of v, because I need both of those numbers right up over here, right? So the trick is, which one's which? What do I pick? So every problem is going to start with a product rule. Pretty much. There's actually one example where it's not a product rule, but for the most part, they're all product rules. So you can pick whatever you want for u and whatever you want for dv. I'm going to actually show you all the possibilities here just so you can see them, and then talk about why I might pick which one. So my first choice is to make u equal to x, my dv equal e to the 2x dx. That's choice number one. Choice number two, don't write all these down, just kind of watch. Choice number two would make u equal to 2x, v equal to x dx. My third choice is actually, believe it or not, to make u equal to x e to the 2x and v equals dx. So I kind of have three choices: dx by itself, or x as x dx, or e to the 2x dx. So these are kind of my three choices. It's hard to know which one at the beginning. It's going to be tricky. You might try the wrong one, and what's going to happen, you'll see, is we're going to get a new integral in my problem. And if that integral is integrable, good, we're done. If we can't do it, we might have to look for another way. So sometimes it can be a little tricky. So what I usually try to say is guess. I like to do this. I like to guess dv first, because what you're going to do is find the antiderivative of dv, right? Whatever you pick for dv, you're finding the antiderivative. Whatever you're picking for u, you're finding the derivative. I think most of us would agree taking derivatives is easier than taking antiderivatives. So what I want to do is make this as complicated as possible, but still be able to integrate it. So it is a real skill to figure out which ones work. And first of all, you might even think the u substitution would work, right? So it's like, whoa, we got all kinds of stuff going on. So I'm going to erase this and go right back to this one, because this is the one I'm going to try. Integration by parts often sometimes called a reduction formula. It reduces the x's. So I'm going to pick my u to be x, my dv to be e to the 2x. By the way, again, this could be a u substitution problem. So why do I have to do integration by parts? Why not do u sub? Well, if I do a u sub, just let me do this real quickly. Don't write this down. I'd probably make u equal to the 2x, right? The inside part of the composite function. But that means du is 2 dx. Notice I still have an x in there. I still got a little bit of a problem, right? So u substitution just doesn't work. So here's how this works. Once I pick my u and my dv, I cross my fingers and I hope I got the right ones. I take the derivative of u, which is dx. I take the antiderivative of dv, which is e to the 2x over 2. And then I rewrite using this formula. So the integral of x e to the 2x dx equals uv, u is x, v is e to the 2x over 2, minus the integral of v, which is e to the 2x over 2, du, which is dx. So notice I've just changed the form of the problem from one integral to another. However, notice in the second integral now, it's not a product rule anymore. It's just a pretty straightforward integral. By the way, some people always ask this when I integrate right here, isn't there a plus c? There is a plus c, but I'm just going to put that in at the end, okay? If you put it in there and keep working with it, it keeps floating around. So I'm just going to go x e to the 2x over 2 minus, I'm going to factor out that 1/2, leave it alone, and then I just got e to the 2x again, which is another e to the 2x over 2 plus c. So there's my integration by parts. Pick a u, pick a dv, apply the formula, and then take that new integral, okay? So let's pick another one here that looks a little different. They all got little twists in them. So let's go with, wow. Let's go with this one. We're going to go integral because this is a little thing difference going to happen in this one. E to the x cosine x. Something different is going to happen in this one. So I'm going to pick my, in this case, it doesn't actually matter which one you pick for u and which one you pick for dv. They're both going to work out. So I'm going to make u equal e to the x. Remember I said make dv as complicated as you can and still be able to integrate it. So they're both pretty easy integrals. I guess cosine's a little more complicated than e to the x. Du is e to the x dx. The integral of cosine is sine. So now when I apply my formula, integration by parts formula, I get uv, e to the x sine x, minus the integral of v du, which is e to the x there. So guess what? I have to do integration by parts again. On this one, looks the same, yeah? U equal to e to the x, dv equals sine x dx, du equals e to the x dx. The integral of sine is negative cosine. So now, you might be wondering why I keep writing this down, because it's my original problem. I'm always kind of keeping track of that, and you'll see why I'm writing it down in just a second. I get e to the x sine x. Be careful here, minus. So now I got another integration by parts, but be careful with that minus sign. So it's uv, which is negative e to the x cosine x, minus the integral of v du, which is minus e to the x cosine x dx. So if I deal with my minus signs here, e to the x cosine x dx equals e to the x sine x plus e to the x cosine x. I got minus, 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 minus e to the x cosine x dx. So you might be saying, whoa, what the heck's going on? Well, I got another integral there, and look, it's the same integral I started with back to the beginning. But it's actually not exactly the same integral I started with. It's actually a minus, which actually is very clever and very cool. Because remember, I'm trying to find, this is why I keep writing this down here also, I'm trying to find e to the x cosine x. So what I'm going to do is I'm just going to add an e to the x cosine x to both sides. And I'm going to wind up getting 2 times the integral of e to the x cosine x dx equals e to the x sine x plus e to the x cosine x, and then I just divide by 2, and I have my answer. So every once in a while in integration by parts, you wind up right back where you started, with a minus sign maybe. Sometimes there's a constant floating around in front of it. Just treat it like an algebra problem at that point. It's a little bit tricky, a little bit weird. If there were a plus e to the x right here, that would be bad, because when I subtracted it from there, so I would get 0, and then I'd have all kinds of problems, which means I probably made a mistake. Or I might get 0 equals 0, which means I didn't make a mistake. It means I just picked the wrong combination of u's and dv's. And sometimes you just got to guess. So I'm going to give you one more example problem, because I know this video getting a little bit longer. Sometimes you get an integral that only has one term. You're like, I don't know how to do it, which makes sense because you don't know the integral of natural log of x. It's not 1 over x. That's backwards. But integration by parts will actually work on this, believe it or not. You can't do a u sub. There's nothing to substitute. It's not a one-step one. So sometimes if you just see one term by itself, it actually is an integration by parts. Now, I can't put natural log of x dx here, because if I did, I have to integrate it. And if I could integrate it, I might as well just integrate it in the first place, and then I'd have my final answer, right? So remember, one of the options I gave you before was just to make dv equal to dx. You make u equal to natural log of x. The derivative of natural log of x is 1 over x. The antiderivative of dx is just x. And now I get uv x ln x minus the integral of v du. Oops, I lost a dx there. Sorry, v du, which is just dx. But the integral of dx is just x. So we get x ln x minus x. By the way, this one's actually kind of worth memorizing. It shows up a lot. That the natural log of x actually pops up. So you might actually get a natural log of x to pop up in another integration by parts, and you want to just kind of know it. So it's kind of worth memorizing this one. If you don't memorize it, you just have to do another integration by parts. So you can see I had another example back here that just had one term. If there's one term, integration by parts. Seems weird, but integration by parts, same way. Okay. If there's more than one term, then you're just kind of guessing a little bit. It just takes some practice, just like the other ones. The more you do, the more you practice. Don't forget, use subs might still work also. So sometimes you use subs in problems. Any of the old methods might work also. So just because we're doing integration by parts doesn't mean it will be integration by parts. There are other methods that might work also. So that's it for integration by parts. I'll see you in class.